Okay, good morning. So let us quickly recall what we studied in the last lecture. We assumed a latent variable model. That means we are actually observing some X set of variables about the data, and X may be the input, some of X may be input, some of X may be output. So it might both be a conditional model as well as a generative model. So we are observing X, but we believe or we model in such a way such that X is generated from another latent variable Z. But Z is unobservable. Z is, you don't have the value of Z whatsoever. In fact, for that matter, Z is kind of unreal. It doesn't exist. It doesn't exist. We are just having it for our convenience. Or maybe if it exists, it is not observable. And we can only observe X. And both X and Z are, their distributions are governed by some parameters, distribution parameters. Let's say theta for X and phi for Z. And what we are sort of interested in is the joint distribution of X and N. Even though, X and Z, even though Z is unobservable. One thing you observe is that what we finally have is a set of observations X1 to X capital N. And there is an underlying Z1 to Z capital N, one for each observation. So this, the point is to be noted. So it is a kind of a variable in the sense that for every standing instant xi, I have a value of zi, which I don't know. And so we have seen many examples of this modeling where it's beneficial to have such an additional variable z, and we show that there are several examples. For example, we can have a Gaussian mixer model where every data comes from one of the three Gaussian, and so the final distribution of the data can be written as this, and then the parameter of the distribution are the mixing coefficient, the mu and the sigma, one for each Gaussian, one for each of the capital K number of Gaussians. And we found that what we can the latent variable that we can associate for every training instance or test instance xi is a variable called zi, which means it sort of gives us the cluster belongingness of xi to or the Gaussian to component 1, the belongingness to component 2 in this way to the belongingness to component k. Okay, so z is basically this vector. But note that per se in the training data, nowhere we mention of this gamma 1, gamma 2, gamma k. Nowhere we say the training data is just a collection of points. Nowhere this red point belongs to component 1, or the red point has this gamma 1, gamma 2, gamma 3, and so on. We never say that. It's not mentioned in the data. So it's a latent variable. But nevertheless, we can sort of, if we know the distributions of these individual Gaussians, we can find out gamma 1, gamma 2, gamma k. So that's actually easy to find out. So this gamma 1 is kind of probability of belonging to xi belonging to Gaussian 1. So gamma 1 would be something like pi 1 in xi mu 1 sigma 1. Similarly, gamma 2, similarly, gamma 3. Okay, so these latent variables, if we know the distribution of these components, they can be calculated, they can be computed. But what we are finally interested in is kind of a set of parameter values, uh, pi1, pi2, pi3, and a set of pi3 and mu1, mu2, mu3, sigma 1, sigma 2, sigma 3, such that the this is the important point. You can best explain the data. So x is the x1 to xn. Best explain the data if we call this entire set of parameters as theta, given certain value of theta. So we are interested in this maximizing this likelihood. It best this particular theta best explain this x. So since this is the likelihood, this obviously would be called theta MLE. So in this case, theta MLE would be given a value of pi k, mu k, sigma k, a set of values of pi k, mu k, sigma k. What value maximizes Px given theta? What value maximizes Px given theta? Not for a single xi, for all the xi, for the entire capital X, which is a collection of x1 to xn. And we thought that we showed that this can be sort of thought of as an alternating optimization problem, in the sense that first we fix your pi, mu, and sigma to certain value, calculate z, and using z, once you know z, you can find the likelihood, and sort of find out that particular z which gives you the highest likelihood. And then in the first step, called the E step, and in the second step, fixing your z or a particular. So first thing is that you fix your value of pi, mu, sigma, and find out which value of z, which realization of z maximizes this quantity. Okay, and the second step, fixing this particular z, find out which is the value of pi, mu, and sigma, which maximizes this kind of pz kind of thing. We'll come to that. That's the M step. And we sort of alternated between these two till the value of the likelihood converges. And this gives us the value of pi, mu, and sigma. So we know the GMM. We know the parameters of the GMM. We have estimated the parameters of the GMM. So this algorithm, as I had mentioned, is called the expectation maximization algorithm. It's the expectation maximization. It's actually a general optimization technique for probabilistic inference. It's not just used in GMM, it is used in many other situations. So what we will do today is to explain what is called a generalized EM algorithm, and we don't just restrict ourselves to Gaussians. We show that for any kind of mixer models or distributions or any other estimation problem or inferencing problem, this optimization technique can be useful. All right. So before I explain the generalized EM algorithm, I'll need two mathematical results to derive the algorithm. Okay. So the first result is about something called a concave function. So here is an example of the concave function. So the concave function has the property that if you take any 2 points A and B, and you take a third point, which is a combination of A and B in the following manner. That means you take any alpha greater than equal 0. If you take any alpha greater than equal to 0, if you take this vector A, or this point, in this case A is a scalar, This in general, it can be concave function of multiple variables also. You take any alpha times a plus 1 minus alpha times the second point, you get a point in between. You change your value of alpha, you get points in between, lying on the line connecting FA and FB. So this is FA and this is FB. Okay, so this is a point connecting these two lying on the line connecting these 2 points. All right, and so what is the x value of this point? The x value of this point is, sorry for this, is this quantity. This point is alpha a plus 1 minus alpha b. That's this point. And what is this point? Then it is kind of it is a point lying on this line. Okay, so it is a you can see this point I can actually express as alpha fa plus 1 minus alpha fb. Okay, it is a combination of this height, which is fb, and this height, which is fa. So this will be the combination. This is easy to derive. I mean, too easy to derive actually. I'm not showing it. So that is the value of the y-axis at this point. Now what we do is that we look at f of alpha a plus 1 minus alpha b. Look at this point. If it is a convex function, if it is a concave function, it means for all values of alpha, this quantity will lie above this quantity. The line connecting 2 points will lie below the curve. Below or equal to the curve. So for any concave function, we have this property. F of alpha a plus 1 minus alpha b greater than equals alpha times fa plus 1 minus alpha times fb. I think you have heard about convex functions. So this is just the reverse of a convex function. It's a concave function. In fact, it's easy to show that if fx is concave minus fx is convex. This can actually not just be restricted to not just be, let me try to delete this. Not just restricted to, yes, not just restricted to 2 points. I can actually extend it to multiple points also. So if I have another point C, and this is my C, and another point D, this is by D, and this is by C. And then we have a corresponding set of alpha. This is my D, alpha 1, alpha 2, alpha 3, alpha 4. In general, I have this result. Alpha 1, A1. Okay, not A, B, C, D. Let's call them A1, A2, A3, and A4. F of alpha 1, A1, alpha 2, A2, alpha 3, A3. You can increase more points also. Is greater than alpha 1, F of A1, alpha 2, F of A2, alpha 3, F of A3. Provided the alpha 1 plus alpha 2 plus alpha 3 adds up to 1. Okay, if they add up to 1, this general result also holds. Okay. So why are we, so you can actually intuitively think of like this. So you can do pairwise actually. You can take a combination of A and C, which lies in between. So it's A and C is something like this. You take any point in between, combine that with D, and so you can keep on, and still it will lie below the curve if it is a concave function. Okay, so there are many concave functions. For example, one of the most common example, logarithm is a concave function in the interval 0, 1. It's a concave function in the interval 0, 1. Right. So let us see. And of course, this you can already probably guess that we work with log likelihoods. And the log likelihood is kind of log of some probability value. And px lies between 0 and 1. So this log likelihood function is a concave function. All right, so this is one more thing. The second thing is that why are we wait. Yeah. Okay, so why are we talking about extending it to multiple alpha 1, alpha 2, alpha 3? See the property, I have already said that alpha 1, each of the alphas actually should be greater than or equal to 0, and the sum of the alpha values, sigma alpha I, should be 1. So this means that these alphas look like something like a probabilities. So I can also think of alphas as probabilities. Okay, so this is kind of the probability that the x takes a value a1. This is kind of probability that x takes a value a2 and so on. Okay, so it's like a probability. So what does this quantity mean? What does this quantity mean? Let us define, suppose I have a probability, suppose x is distributed according to some probability distribution P. Okay, and say x takes on certain values. So x takes on certain set of values. So what is the expectation of x as per the probability distribution P? We'll use this notation. It is summation x taking on certain value. Let's say x takes on value xi, multiplied the probability that x takes on value xi divided by all the probabilities. This goes to 1 because it is a probability density function. So expectation is summation x takes on probability that x takes on value xi into the value xi summed over all possible values of xi. Okay, summed over all possible values of xi. This is the expectation of the random variable x. Suppose x takes on 3 values. Suppose x takes on values a1 or a2 or a3. And let's say their corresponding probabilities are alpha 1, alpha 2, alpha 3. So what is the expected value of x? You will easily see that according to this definition, the expected value of x is this quantity. Expected value of x is this quantity. Alpha 1 into a1 plus alpha 2 into a2 plus alpha 3 into a3. What is the expected value of fx? It will be alpha 1 f of a1 plus alpha 2 f of a2 plus alpha 3 f of a3. This will be the expected value of fx. So this quantity can be written as expected value of fx. This quantity can be written as the expected value of fx. So fx takes a value fa1 weighted by probability alpha 1, fa2 weighted by alpha 2 and added up. And so what is this quantity? This is f of within bracket expected value of x. All right. So see now if we sort of increase your a1, a2, a3 so to all possible values that x can take off. So what will happen in general? So if we take all possible value of x in some interval, this summation will become an integral. This summation will become an integral. Okay, and if it is in the continuous case, in the discrete case, it will still say a summation. And we see that if f is concave, then f of expected value is greater than expected value of f. This is something called a Jensen inequality. Okay, so I have written down the statement for a convex function. The reverse holds for concave functions. So the Jensen inequality, what it says that if f is concave, then if f is concave, then f of expected value of x, let us see what f of expected value of x is greater than equal to expected value of fx for all p on x. For any probability distribution, this holds. Okay, for any probability distribution holds, if f is concave, then the f of ex is greater than equal to e of fx. Okay, this is called the Jensen inequality. This sort of helps us in the sense that, so now we have a lower bound on f of ex. This e of fx is kind of a lower bound on f of ex. Okay, so if you kind of plot f of ex, you kind of plot f of ex and you plot e of fx. Well, what am I doing? Anyway, it's below this. It's below this, right? So it's a lower bound. All right. So this is a result that way. This is a very famous inequality which is used in a lot of reasoning, in probability, lot of probabilistic reasoning. But remember this statement: f of ex is e of fx for all p. This is also important. For you choose any probability distribution on x, this holds. Okay, so now let us come to the second tool that we will need. Note one thing that even though I have shown it for a summation, if x is continuous, this I can change this summation. I can change this summation to integration. So e to the power epx, if x is continuous, can also be px x dx, and x varying over the domain, x varying over the domain. Okay, so this can become an integration also. All right. So now let us come to the second tool that we will need. It's called the Kullback-Leibler distance. Let me explain. So this is a similarity between two distributions. This measures the similarity between two distributions. So let's take an example. Suppose I have x and I have one px, one distribution, and another distribution qx. Okay, so how do I find the dissimilarity or distance between px and qx? What I do is I pick up a point. I measure the value of px at that point. I measure the value of qx at that point and take their likelihood ratio px by qx. So if the likelihood ratio is 1, for example, here the likelihood ratio is 1 when two distributions are same, two values as probabilities are same, right? And we take a log of that. We take the log likelihood ratio. This is called a log likelihood ratio. You see that since log of 1 is 0, if px equals qx, this will be 0. Okay, so this is for a single point. This is the log likelihood for a single point. We add up log likelihood over all the x. We add up like log likelihood over this quantity over all the x. And not only add up as such, but what we do is that we give more importance to the likelihood ratio for the region of x where density of x is higher. So here x is as a high density. So higher log likelihood here, log likelihood ratio here, it contribute more to the KL divergence. Whereas maybe here or here, maybe something here, px is small. So a high log likelihood ratio in this region wouldn't count so much. So we weight it by the probability values. And again, I mean, after weighting this, you sum it over all possible x, and this gives you the similarity or dissimilarity rather between two distributions P and Q, called the Kullback-Leibler divergence. Note that this is not symmetric in the sense that if you interchange P and Q, you don't get the same expression for KL. It's like P is called a reference distribution, whereas Q is called a comparing distribution. P is a reference distribution. With respect to P, you measure Q. Okay. One thing you can understand, if Px equals Qx, if at all x, if Px equals Qx for all x, actually not for all x, if it's for all x in which Px is greater than 0. If Px is equal to 0, it doesn't matter. This is called the overall finite measure sets. Measure is the probability. Okay, so if Px equals Qx, so what it basically means, if the distributions are same, let's say in all the places except for a single spike, where the probability of which is 0, then also the Kullback-Leibler is 0. But let's forget about such extreme cases. And in general, the Kullback-Leibler measure is 0 if P identically equals Q. If P identically equals Q. Right, and we denote it by this symbol, P. All right, so can you tell that why it is greater than 0, greater than or equal to 0? Equal to 0 if they're equal, fine. But in general, can anybody tell why it will always, but I also claim that this quantity will always be greater than equal to 0. Let us see why that happens. Right. Okay, so let's see why this is greater than 0. If we 1 minute, just. Yes, I think now I'll be able to read. Okay. So let us call this quantity as this entire quantity as some, let's say y is a function of x. Let's call this y as a function of x. And then we think, let's say x is distributed according to px. Okay, so what is this quantity? This quantity is nothing but the expected value of yx, where y is defined this way. This is the expected value of yx. Okay, because see, I am taking a value of yx, I am weighting it by, so it's like px yx dx over all possible values of x. So this is the expected value of yx, where y I have defined to be log of px by qx, right? So by Jensen inequality, what is this? This is greater than expected value of thing is y of ex, where y is a function. Y is a function. I should have told this as f, not call it as y, where y is a function. So this is greater than this. So let me see. Let me delete this. Okay, so this is greater than equal log of, so what is log of expected value of x? Okay, did I make a mistake? Yes, I made a mistake. Let us do it like this. I actually made a mistake. Wait, ignore the earlier derivation that I did. I made a mistake. That's not y actually. Let us do something. Let us write this as integral over x px by qx, where q is some another distribution, into kx by log of px by qx dx, right? And call this thing wait a minute. Wait a minute. Wait a minute. How do I? How do I do it? Wait a minute. This is this. So if I write the Jensen inequality, it will be this is the expected value of fx, so it will be.
So I believe we can reverse the log, as in minus log qx by px would do it. because then
minus
px would get cancelled when you transform log qx by px into like using Jensen's inequality.
yes, right, exactly. So that's the way to do it. Yes, so let us invert this. Let us invert this. That's right. So if we write the negative of this thing, so it becomes minus px log of qx by px dx, and then if we apply the Jensen inequality, it becomes minus, it's greater than equal to minus log of so it's the extracted value comes inside the log, so it's log of qx into px by px dx. If we bring this inside, and px cancels out, so this is greater than equal to minus log qx dx over x, and since this is a distribution, this is equal to 1, so this is greater than minus log 0. Okay, maybe I have made a problem with the sign, I think, and so that oh sorry, why minus log 0, minus log 1, so which is greater than equal to 0. So I think that's the way, that's the right way. Anyway, so the one thing I wanted to demonstrate is that if we apply the Jensen inequality, so what the exercise that we are doing, so it's kind of, we are converting many of these integrals to the form of an expectation, with some probability and some function f. We are converting to the form of an expectation, and then we are applying the Jensen inequality. Okay, so this is a trick that we will keep on doing. This is a trick that we'll keep on doing, and then that what the trick helps us, it gives us lower bounds on these quantities. Right. So anyway, so the summary is that Kullback-Leibler distance is a way of measuring distance between two distributions, and then the smallest value it can take is 0. Otherwise, it will have a positive value, and it is equal to 0 when the two distributions are exactly equal. All right. So now I think we can derive the generalized EM algorithm. So let me work on that. Let me work on that. All right. So we have a latent variable Z. So now I am back to my latent variable modeling, and we have a observed variable xi, zi generates xi, influences xi, right? And we have a set of parameters theta which models xi. And what we said that our job is to estimate given a set of observations x1 to xn, estimate theta. Let's do an MLE estimate, most likelihood estimate, which says that this is nothing but the value of theta which maximizes this x given theta. That means that value of theta which maximizes the log likelihood, which best explains the set x1 to xn. Right, this is our task. We'll estimate this. But we have so far not spoken about our latent variable Zi. What we do is that we see that this is equivalent to optimizing log of. So it's the usual practice. Instead of maximizing likelihood, we maximize log likelihood. So this also, you know that this can always be done. Okay, so a log is, this can always be done. So now let us factor in the latent variable. So we don't know the value of the latent variable Zi for a given value of xi. So what we can do is we can view of this quantity as a marginal with respect to the latent variable. So we can think of this quantity as, I'm dropping the argmax. I'm just dropping the argmax, just writing down log of all the values that latent variable can take, and then the joint distribution of Zi and xi given theta. This is basically marginalizing on Z. Okay, so so this you all agree. So I can write up P of x given theta as summation over all possible values of Zi, P of the joint distribution Zi xi given theta. What does this mean in terms of the Gaussian mixer model? So Zi, you remember, was the vector of xi belonging to component 1, component 2, and component 3. Okay, so this would be the joint distribution of Zi taking on a set of values, say 0.9, 0.1, 0.05, 0.05, Zi taking on some value, and correspondingly xi taking on some value given theta. And this Zi would be for different values. So Zi, it would be Z1. What is the probability that Z1 takes on this value into the probability that Z into the corresponding value that xi takes, Z2 takes. So this is for, if we have 3 Gaussians, it is for I equal to 1, 2, 3. So if we call that as say k as the component, so k takes on value y equal to 3, and this z becomes k, zk actually. So we are taking all possible values that z can take. Given that z takes on that particular value, so I can write it as z equal to k, jointly with xi taking on certain value given a value of theta. And this we add up over all possible values that z can take. Right. So what basically we are doing is that we don't know Z. So as if we are adding up the joint probabilities over all possible values of Z. And then we get the marginal probability X given theta. All right. So this is the first thing we are doing. The second thing is that, so I think this is acceptable. So, and the second thing that we are doing, this is for a given value xi. And but this is for the entire set X. We assume x1, x2, xn to be independent. If they are independent, I can multiply these probabilities over all xi. So if it's this given xi would be p of z equal to k1 into x1 given theta into p of z equal to 1 into x2 given theta, and so on. So it is a product because they are independent. And since you are taking a logarithm, the product becomes a sum. So basically we have argmax over theta . argmax over theta. Actually, this will also be a probability. So this sum, I made a mistake. This will come outside. This is not a sum. Oh no, this is a sum. Oh, wait. So, but over n I equal to 1 to n. This is for all the examples because they are IIT. Log of sum zi over all possible values of zi. Let me write down as 1, 2, 3 for 3 Gaussians. P of zi comma xi given theta. Okay, so this is what we want to maximize. This is what we want to maximize. Okay, so the MLE problem is the following. So what we do is the following. You look at the joint distribution of zi and xi, marginalize the joint distribution over all possible values of zi, which means summing them up, take the logarithm, and then add up this logarithm for all xi from 1 to n. That is your entire x given theta, log of x given theta rather. And we maximize that with respect to theta. Right. So in practice, what we'll do is that, for example, in the Gaussian model, we assumed some form for P of zi xi. We assumed them to be Gaussians with some mixing parameter pi I. We assume them to be Gaussians. Okay, so P of zi xi usually will be assumed or given. In the Gaussian mixer model, this is a Gaussian. This is one of the component of the Gaussian. If you fix z to be 1, it is the first Gaussian. If you fix z to be 2, it is the second Gaussian. But we add up over all of them for marginalizing. Okay, so that will be known. And then, so if we know this value, finally we'll get a expression like this. But if for the general case, this entire expression might be pretty complex, and it's usually not possible to solve this, to get a closed form solution of this optimization problem. Right. So rather numerical solutions are more useful. Okay. So this is what I was talking about. So what is that? If we have the set of parameters theta, it is what I am maximizing is summing up x and zn, the joint probability over this, which is same as log of p zn given theta and plus log of p xn given zn theta. Okay, so this is just if you express it, if you express this as product of pzn into p of xn given zn, it will take this form. This is what we are maximizing. So we are actually maximizing this quantity, as I have explained. This quantity, as we have shown, is a marginalization over possible values of z. In general, this is not a closed form expression. It is not a simple expression. So what will happen is that if you kind of so you have to numerically solve it. If you plot theta and log of p x given theta, usually it will be a pretty complex function like this with a lot of local maxima. It will be a complex function. And what we are interested in is to find the highest point of this function. So that is our optimization problem. Okay, so this is you can actually solve this optimization problem by things like gradient descent and all this, but gradient descent have their problem in the sense that they get stuck in local minima and so on. So now let us look at an alternate way of, so expectation maximization is just an alternate way of solving this problem by a method known as alternating optimization. A method known as alternating optimization. The general principle is like this. If you have a function of say 2 variables which you want to optimize, what you do is that fix one of the variable, maximize with respect to the other variable, obtain a candidate solution. Now for that candidate solution, fix the first variable. Now change the second variable to maximize, given the first variable to be constant. And this you do over several iterations till you convert. So what we'll do here in order to solve this optimization problem is the following. What we'll do is that we will use a slightly different trick known as variational optimization. This method is known as variational optimization. So in normal calculus, what you do, you find the maxima by taking the derivatives. Here you do by something called a value, which can be shown to similar to anyway. I'll come to that details later. So what I will do is that instead of optimizing, there's a log here. Instead of optimizing this complex function, I will lower bound this. I'll kind of lower bound this by a function. I'll obtain a lower bound of this function. Okay, and maximize the lower bound. Maximize the lower bound. And the lower bound, of course, will have the property that first of all, it is a lower bound. Second of all, it is a function which can be easily optimized. It is a function which, so for example, it might be a convex function or it might be as a quadratic function, some function which is easy to optimize. Let's say convex function, easy to optimize in the sense it has a single global maxima and so on. But the problem is that it is a bound, it is a lower bound. So just optimizing this is not good enough for optimizing the original function. So what we do instead is that we'll not take a single lower bound, but take a family of lower bounds. We take a family of lower bounds, and over iterations successively. So it will be a nested kind of loop. In the outer nested loop, you will choose one lower bound, and in the inside nested loop, you will optimize this, take the highest point of this lower bound. Then in the next iteration, in the outer loop, choose another lower bound, and in the inner loop, choose the highest point of this lower bound. Okay, so this way we'll keep on. But the thing is that, so we are choosing over several lower bounds. So we'll say that the lower bound is, say, another distribution, which we call Q. And it is a function of two things. It is kind of a local distribution. It's not a global distribution. It's a local distribution. That means this distribution is locally a good approximation of the original distribution. And the local approximation depends not only on theta, but some local variable, latent variable Zi. So the distribution is Q is a function of Zi as well as theta. You change your Zi, you get another local distribution, another in the family of the distribution. Okay, and we'll see we'll use the property that this local distribution is a lower bound on the global distribution, which you are actually trying to optimize. Right, and we'll do in such as we'll soon derive what this lower bound Q is, but let us first understand the basic principle. Okay, the basic principle is the following, that when you are trying to optimize a function, so let me explain the process, what will actually happen. What will actually happen? So what I will do is that I'll start with a arbitrary value of theta. Let me call as theta naught. I'll start with the arbitrary guess of the solution. Well, this I have already, I'm near the solution. Let me draw another figure. This is theta, and this is log of px given theta. Okay, so I will start with some guess of theta naught. Guess of theta naught. All right, so then I'll find a value of, say, Z1. And I will try to find a Q Z1 given theta, Z1 given, or let me write it, given theta naught as some lower bound which is as close as to the original function in at the point theta naught, as close as to the original point in the function theta naught. So drawing is not very good. Okay, so this is, let's say, my theta naught. I find as good as an approximation of theta naught as possible. So this is my QZ naught, theta naught. Okay, so the first optimization problem to be solved, which I call as the E step, is the following. You find a Q so that at theta naught, the gap between Q and this P of log of P of X given Q, this is as small as possible. So the lower bound is as tight as possible at theta naught, not at other points, only at theta naught. Okay, so this is the E step. All right, so maybe out of this and this and this, you come up with this. You solve for, you get this Q at Z naught. So note that Q is parameterized by both Z and theta. So you have to, so fixing this Q is equivalent to fixing a value of Z naught. Assuming, so the functional form of Q is constant, only Z naught changes. So it's equivalent to finding a value of Z naught. Once you have found this small gap or minimum gap Q, what you do in the next step, which we call the M step, is move to the highest point of Q, which is this. Move to the highest point of Q. And this you call as theta 1. This you call as theta 1. All right. So in the next step, what you do, you look at theta 1 and try to get another Q which best approximates P log of P at theta 1. Let me change the color. So get another Q which best approximates at theta 1. So among all these, get a Q. Now fix that theta 1. Now move to the, let's call that QZ1 theta naught. And in the next M, that is your E step. In the M step, move to the highest point of QZ1 theta naught. Move to the highest point of QZ1 theta naught. Call that as theta 2. Okay, and keep on doing this iteratively since you see the go to the maxima. Actually, this is called the method of alternating optimization. I think some of you might remember something called a Newton-Raphson method. Newton-Raphson method. So what has done, I'm explaining with the minimization problem. What has done in the minimization problem is that at any point you choose a line which just touches this curve. What it means, touches means the gap is 0. You make the gap between, and see this straight line is kind of a lower bound on this function. If it is a convex function like this, it's a kind of a locally lower bound kind of thing. That means the straight line lies below this curve. It's a lower bound. And among all possible straight lines, we take the one in which that at this particular point, the gap between the straight line and the actual curve is 0. Okay, now you take that as the approximation and move to the 0 crossing point. You move to the lowest point of the straight line. Okay, so now this is your next case of the solution. There fix another straight line, which is has a gap 0. It's still a lower bound. Move to another point, to the lowest point of the straight line. That is your guess 2. Okay, this way you come to the minimum. Okay, so what we are generalizing here is that instead of taking a straight line, I am taking a general lower bound, any lower bound. And I am making the lower bound gap with the actual function as small as possible. So here you can see actually this, how did I minimize this gap? It was nice close form there. I just took the derivative of this function to get the line, the gradient of this function. So here it will be slightly more complex. The gradient will be slightly more complex, but we still try to make it the gap as small as possible and the highest of that function. Here it is no longer a line, but it's a general function. All right. So then and keep on doing this till you go to the solution. So this method is known as the method of alternating optimization. With the help of another auxiliary lower bound. Okay, so the EM algorithm, in fact, this Q is called a variational distribution in the sense that it changes with Z. It's called a variational distribution. It depends on both Z and theta. And this entire method of optimization is also sometimes called a variational optimization method. So let me take a quick 5-minute break. Then we'll see how we can apply this variational optimization method to the problem of estimating the maximum likelihood estimate of theta in a latent variable situation. I think you can already guess now this family of variational distributions Q that we get will be parameterized by the latent variable. You change your latent variable, you get a separate distribution. You get a separate distribution. I think let me just to make the view clear, let me also revert back to this. So it's this individual ellipses that I drew. These are actually the variational distributions Q. So the variational distribution in this Q is N1 is one variational distribution, which is Q1. Q2 is this second normal. Q3 is this third normal. And which distribution you will use to, if your data falls here, Z equal to first cluster, you use this distribution to estimate. If your X falls here, Z equal to 2, this is your variational optimization. If Z equal to 3, this is your Q3. So you change your Q as you move the data point, as you choose your different data point as affect the latent variable point, right? So we are fitting this local distribution, and so Q1 is this N1. So now next what we are doing, we are find the best estimate of N1, the highest point of N1, that parameters of N1 which maximizes the likelihood of X1 given Z equal to 1. Given Z equal to 1, fixing your Q to be that for that particular Z, find out the value of theta which maximizes the likelihood. And this we are doing successively for all different points. So this is kind of the setup. Let me take a quick break. I'll pause the recording and then we'll derive it for the case where in the general setting. So I come back